So let's go ahead and use the trapezoidal rule to approximate an integral. So suppose you have an integral from a to b of some function f of x, and you want to set up how much area do we have from a to b, approximating the area. So sometimes it could be an over approximation, sometimes under approximation, depending on how many trapezoid you create. So this is the formula, the delta x over 2. Then you have all of these height. So the first height and the last height, they're just the height, no multiplied by any coefficients, but the ones in the middle, you multiply them by 2. So let me show you a little bit of background where we get the formula from, just so that you know why this is the formula. So this is our function, some f of x equals y, and say you want to approximate how much area we have from, let's say, from A to B. So we create a finite number of trapezoids and add them up. So let's say this is your first trapezoid. So from first height to the next, and this thickness right here, that will be delta x. So we know for trapezoidal rule, you find the area by doing 1/2 base 1 plus base 2 times height. So that's the area for a single trapezoid. So if you look at this trapezoid, so this is your base 1, this is your base 2, and the height is, of course, delta x. So using the function notation we have, so we can say that b1, this will be the height at f of x naught, and this will be the second one, base 2, that will be evaluated f for x1. So using that geometry, we can say that this would be 1/2 times base 1, well, that's at f of x naught, plus base 2, that's f of x1, times the height, well, that's the thickness, so that's delta x. So that's one way you can see why this is the derivation of the formula. And then for the next trapezoid, again, you create one right here. And again, this will be your base 2 and base 3, and so on. So you get the idea. You go all the way up to the last one, creating finite number of trapezoids. When you add them up, you get this formula. So delta x divided by 2 times y naught plus 2 times y1, and so on. And the last one, again, yn, that doesn't have coefficient in front other than 1. Now, let's go ahead and try this to approximate an area under a curve for a specific function. So we want to use the trapezoidal rule to approximate the value of this integral using n equals 4. So let me show you the picture, how it looks like. So x squared minus 1, so that's a parabola shifted down 1 unit. So this is your f of x. So when x equals 0, it's going to be at -1, and then it will just curve like this. So something like that. So it's a parabola like this. Of course, there's curve this way, but we're not interested on that side, only from 1 to 5. So this is 1, and let's say this is 5, just approximating. So let's just call that 5. So here's, so we want to know how much area is right here by using n equals 4. So we're looking at the interval from 1 to 5. So if n equals 4, that means you're doing 4 partition of this interval. So 1, 2, 3, 4. Let's find delta x. So delta x, it's going to be b minus a over n. So for this problem, this is your a, this is your b. So it would be 5 minus 1 over 4, because n is 4. So that would be 4 over 4, that's 1. So the thickness of each trapezoid would be 1. So it'll be 1 plus 1, that's 2. 2 plus 1, that's 3. 3 plus 1, that's 4. 4 plus 1, that's 5. So let's draw it right here on the graph now. It says 2, 3, 4. So these are your x sub naught. This is x sub 1, x sub 2, x sub 3, and x sub 4. Now let's draw a trapezoid under the curve. So the first trapezoid will look something like this. So that's one of our trapezoid. Then the next trapezoid will look like this. And then the next one would look something like this. And the last one will be right up here. So not the best picture, but at least you have an idea what we're doing with this. So call this T1, T2, 3T, T4. So we're adding them up. Now let's find their height. So the formula for the trapezoidal approximation, so we're using 4 for n. This would be delta x over 2 times f of x naught. So the height on the first entry plus 2 times the second entry, so f of x1 plus 2 times f of x2 plus 2 times f of x3. And the last one, this one, we don't multiply that by 2. So the first and the last, you do not multiply by 2. So this will be 1 times f of x4. So that's the setup for the trapezoidal rule. Now our x1 is right here. So x naught is 1, x1 is 2, and so forth. So let's plug them in. So this will be delta x. Delta x is 1. So that's also right here. We computed that. So it's 1 over 2 times f of x naught. Well, x naught is 1 plus 2 times f of x1. That's 2 plus 2 times f of x3. So the f of x2, that will be 3 plus 2 times f of x3. That would be f of 4. And the last one, f of 5. So keep in mind that these, the first term and the last term do not get multiplied by 2. So now let's plug this into our function and find their y values. So this would be 1/2 times f of 1. So if you plug in 1 into your function right here, so you find the y value by plugging it into whatever function you have. We have x squared minus 1. So this would be 1/2 x squared minus 1. So that would be 1 squared minus 1 plus 2 times, again, x squared minus 1. So x is 2, 2 squared minus 1 plus 2 times, again, x squared minus 1, 3 squared minus 1 plus 2 times 4 squared minus 1 plus 5 squared minus 1. So that's the setup. Now let's find this value. That's your approximated area, just 1/2. So this will be 0 plus 2 times 2 squared minus 1, that's 4 minus 1, that's 3, plus 2 times 3 squared minus 1, that's 9 minus 1, that's 8, plus 2 times 4 squared, 16 minus 1, that's 15, plus 5 squared minus 1, that's 24. And then if you go ahead and add these up, you have 1/2, 6 plus 16 plus 30 plus 24. And this will be about 39. So that's the approximated area under this curve. And you can see that it makes sense because our trapezoids are a little bit over the curve. So it's a little over approximated. Well, let's go ahead and find the actual area since we do know how to integrate this function. So let's go ahead and do that. So now let's find the actual area. So we're looking at 1 to 5 of the function x squared minus 1. Using the power rule of integration, this would be x cubed over 3 minus x, evaluating from 1 to 5. So plug in the upper limit of integration. You have 5 cubed over 3 minus 5 minus lower limit of integration, 1 cubed minus 1. And then if you simplify this, you will have 125 over 3 minus 5 minus 1/3 plus 1. And this will give you, so these I can combine them. That'll be 124 over 3 minus 4, negative 5 plus 1. And this will give you about 112 over 3. That's approximately 37.3. So that's the actual area. And the one we approximated is 39. So not so bad.